Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Process control measuring instruments, types of temperature sensors and their applications. In this video course, you will learn the importance of measuring instruments and what is temperature sensor, field system thermometers, electrical system thermometers, radiation type or infrared temperature sensors, infrared thermography. Please subscribe to the channel. By subscribing, you will motivate us to produce knowledgeable video content for you. So subscribe now before you forget. The first step in process control is the measurement. Anything which cannot be measured cannot be controlled. The measuring element is called the instrument. Not just the measurement, but measuring with accuracy is key to reliable operation and control of the process parameter at the desired value. The important process parameters which need measurement for process control are temperature, pressure, flow rate, level, concentration, etc. Temperature is an important and critical parameter in many processes. The processes need accurate and reliable sensors to measure the temperature not only for monitoring purpose but also for control function. What is temperature sensor? Temperature sensor is an instrument that is designed to measure and indicate the temperature in a specific application. These applications varies from measurement of temperature in utility services to furnaces, boilers, reactors, distillation columns, etc. There are several types of temperature sensors. The choice of temperature sensor for a given application depends most importantly on the characteristics of the sensors. Temperature sensors are broadly classified under two categories: field system thermometers, electrical type thermometers. Field system thermometers. A field system thermometer, also called dial thermometer, is a temperature measuring instrument consisting of the following: a thermal system and an indicating system. A thermal system is a closed system filled with temperature sensitive fluid and has the following components: a bulb, an expansion device, a capillary tube connecting the two. There are four types of field system thermometers used in the industrial applications depending on the thermal system: liquid filled thermometers, vapor filled thermometers, gas filled thermometers, mercury filled thermometers. The liquid filled system thermometer is completely filled with liquid and works on the principle of expansion, that is volume increase of the liquid as the temperature increases. The temperature range of application is minus 210 degrees centigrade to 315 degrees centigrade. Organic liquids, pentane and butane, can be used as liquid for this range of application. Typical applications include food and pharmaceuticals, where mercury filled thermometer cannot be used. Vapor filled thermometer. The vapor filled system thermometer is partially filled with volatile liquid and works on the principle of increase of vapor pressure of the liquid as the temperature increases. As the vapor pressure increases, the Bourdon tube expands. moving the indicator. These systems provide quite accurate measurement. The liquid for the system is selected depending on the temperature range of the measurement. Ethane, acetone, ethyl benzene, and ethyl chloride are used as liquid. With ethyl chloride, the temperature range of application is 40 degrees centigrade to 175 degrees centigrade. Gas-filled system thermometers. The gas-filled system thermometer is filled with gas and works on the principle of expansion of gas as the temperature increases. As per the equation, PV equal to N or T. Since the volume of the filled system is constant, an increase in temperature will result in increase in pressure. Nitrogen is usually used. The temperature range of application is minus 210 degrees centigrade to 315 degrees centigrade. Shown in this figure is a gas-filled temperature sensor. It has a stainless steel bulb filled with nitrogen gas and a long capillary tube for remote fixing of the dial gauge. Gas-filled temperature sensors are used for the widest range of temperatures in the filled system category. Applications include chemical processing, control panel, pipeline applications. This figure illustrates a typical applications of a filled system thermometer for local indication of temperature of a liquid flowing through a pipeline in a tank form. Mercury-filled thermometer. In this filled system temperature sensor, the bulb is filled with mercury metal, which expands as the temperature increases. Since mercury is toxic, it is not widely used in industrial applications. Filled system thermometers can be used for direct mounting or remote indications. Gas-filled thermometers can be used for remote indications with capillary length up to 100 feet, whereas liquid-filled systems are used for remote indications up to 25 feet or less. Electrical type temperature sensors. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. Electrical system temperature sensors fall into two categories: thermocouples, resistance temperature detectors RTD. Thermocouples. A thermocouple working is based on SPEC effect. According to SPEC effect, when a closed circuit is formed by joining two dissimilar metals at two junctions, and the junctions are maintained at different temperatures, then an electromotive force EMF is induced in the closed circuit. The amount of EMF produced is different for different metal combinations. The EMF produced is proportional to the temperature difference of the junctions. Shown in this figure is a sketch of a thermocouple consisting of two dissimilar metals joined at two ends with one junction kept at the unknown temperature or the temperature to be measured, and the other junction at the reference temperature. The junction kept at the temperature to be measured is called the hot junction, and the other junction is called the cold junction. The thermocouple wires are chosen so that the EMF produced varies linearly with the temperature. The relationship between the temperature difference and the EMF produced given by ETC is a function of TH minus TC, where ETC is EMF generated by the thermocouple in millivolts. TH is the temperature of the hot junction in degrees centigrade. Tc is the temperature of the cold junction in degrees centigrade. This table presents the typical thermocouple metal combinations and their temperature range. The EMF developed with the thermocouple vary with the metal combination. For example, copper and copper-nickel combination can be used for temperature measurement from -200 to 400 degrees centigrade. Shown in this figure is a thermocouple temperature sensor. Note the cold and hot junction as marked. This figure shows the use of thermocouple in a catalytic cracker unit. Thermocouple is used to measure the metal wall or skin temperature of the catalyst tubes inside the furnace, typically in furnaces and fired heaters. The thermocouple for the hot junction is made in the form of a pad as shown in the figure, so that the pad is fixed to the tube surface by welding or other means. Thermocouples are most common type of temperature measuring instrument used in the industry today. Their wide acceptance is due to the simplicity, ease of use, speed of response to variation in temperature. Resistance temperature detector (RTD). Resistance temperature detectors are temperature sensors that make use of the principle of the variation of electrical resistance of a wire with temperature. The relationship between the resistance of a wire and temperature is expressed as RT equal to R naught times 1 by alpha T. Where RT is the resistance at temperature T. R0 is the resistance at temperature reference temperature, usually at 10 degrees centigrade. T is the temperature of the medium being measured. Alpha is the temperature coefficient of resistance. RTD used in industries are usually made of platinum, nickel or copper. Platinum RTD is the most common type of RTD used in the industrial applications because platinum has excellent corrosion resistance, excellent stability over a long period of time, and can be used for a wide range of temperatures. Platinum RTD is used for temperature range from -200 degrees centigrade to +800 degrees centigrade. Nickel RTD is used for low temperature ranges, typically -80 degrees centigrade to 250 degrees centigrade. However, it has lower stability compared to platinum, and measurement accuracy reduces with time. It is less costly compared to platinum. Copper RTD has the best resistance to temperature linearity and is low-cost material. However, it oxidized at high temperatures and hence limited to temperature range -200 degrees centigrade to 260 degrees centigrade. This figure illustrates a typical RTD temperature sensor. The platinum wire is wound around non-conducting core, which is usually made of ceramic. Lead wires are used to connect the platinum resistance wire to the transmitter. The transmitter converts the resistance measured into a corresponding temperature. A fully assembled RTD temperature sensor is shown in this figure. A typical RTD has a base resistance of 100 ohms at 0 degrees centigrade, increasing to about 140 ohms at 100 degrees centigrade. Though platinum is the most widely used RTD, the major disadvantage is its cost. RTDs are widely used in distillation column in refineries and petrochemical plants. They are the de facto standard for distillation columns. However, thermocouples are used when the temperature of the fluids to be measured exceed the maximum allowable limit of RTD sensors 800 degrees centigrade. We will see some more applications of electrical system temperature sensors in refineries and petrochemical plants. Shown in this figure is a catalytic reactor whose bed temperature is measured by as many as 14 RTDs placed at the top, middle and bottom of the reactor. This figure shows another application of RTD in a multi-stage centrifugal compressor. The compressor has 7 number of RTDs installed in the process loop for monitoring the suction and discharge temperature of each stage. Radiation type temperature sensors, also called infrared thermometers. Radiation type temperature sensor detects the infrared radiation emitted from the surface of the object and measures the temperature based on the amount of infrared radiation. They are the simplest devices and cost less. Infrared is that portion of the electromagnetic spectrum beyond the visible response of the human eye. Because infrared is predominantly generated by heat, it is called thermal radiation. Pyrometer is an infrared remote sensing non-contact type thermometer. It is usually used for measuring relatively high temperatures normally encountered in furnaces and fired heaters. The optical system of the pyrometer focuses on the energy or the radiation emitted by the high temperature surfaces on the detector. The detector is sensitive to radiation. The output of the detector is proportional to the radiation energy emitted by the hot surface less the amount absorbed by the optical system. Since the radiation energy is a function of the surface temperature of the tube, the pyrometer detector output is indicated as surface temperature. Shown in this figure is an infrared temperature sensor. It is the emissivity of the tubes that is used by the pyrometer for measuring the temperature. Emissivity defines the fraction of the radiation emitted by the object compared to that emitted by a perfect radiator, that is a black body, at the same temperature. Emissivity is simply a factor by which we multiply the black body heat transfer to take into account that the black body is the ideal case. Thus, the pyrometer output is expressed as thermometer output proportional to epsilon times T, where epsilon is emissivity, a dimensional number is equal to 1 for a black body. T is object temperature. Infrared thermography. Infrared thermography is used in refineries and petrochemical plants for monitoring critical assets such as fired heater tubes and coils, catalytic reactors, and their refractory conditions. Refractory is a liner material consisting of high temperature resistance material which protect the outer shell of the furnaces, reactors, etc. If the refractory fails, the shell material will be quickly weakened by the inside temperature, which may be in the range of 1200 to 1400 degrees centigrade. This poses a significant risk of equipment failure. Infrared thermography, also called thermal imaging, is used to monitor and survey the conditions of refractory, lined catalytic reactors, piping and fired heaters on a regular basis, and process team uses the data for preventive maintenance if needed. This figure illustrates thermal imaging of a hot air line where the refractory lining has failed. The picture at the top is the actual hot air line piping lined with refractory. The picture below is the infrared thermal imaging of the pipeline, which shows the refractory has failed. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.